All right, we're going to start the next homework problem. We're just going to dive in doing stuff with Morse circle. All right, so you are given some information on an element in the solution manual. They solve it just using a bunch of equations. I'm going to be solving it using the Morse circle. Hopefully it makes more sense this way. But we're just going to jump in. Okay, so you guys will see in the chapter you have Morse circle. This is just a quick diagram of a lot of the dimensions of Morse circle. Morse circle, the point of it was a way of solving these problems back when they didn't have a lot of fancy calculators. Is just an easier method. And so that's why we're going to use it today, just for understanding and whatnot. So in part A, they say the element has a slope of 1 on 2.5. Okay, so that's just this 2.51. Okay, so that is our slope. And if we say we have tangent is equal to just 1 over 2.5, which then means our phi is just going to be 21.801. Okay, straightforward. One thing to notice is in the Morse circle, all the angles are twice as much as what normally exists. So if we were to transfer this to the Morse circle, it would actually be 43.6. Okay, so just jumping ahead. So now if we continue with this, just going to store that out of the way. Okay, so we figured out what phi is, and now we're just going to start solving for our different stresses. Right, so if we go forward, stress average, okay, so in this case, that's where the center of the circle is, right, the stress average, so that's just sigma x plus sigma y over 2, which is just going to end up equaling 14 megapascals, okay? So from there, we're trying to find the radius of this guy. So the radius, all it is, it's the square root of sigma x plus sigma y over 2, this squared, plus our shear squared, right? So those two added together will give us our radius. Okay, so this is just basic geometry stuff. So if we go through this, plug in those, we get a radius of 43, which means the radius of the circle right there is going to be 43. And this is helpful conceptually because if we notice the axis right here, this axis is our shear xy, and this is actually our negative. Down here is our positive axis, and that's just how they've set it up. 0, and this is our stress. This is our positive stress. So positive is actually this bottom half, right? But we see that if our radius is 43, then that is also our tau max, right? So the radius of the Morse circle is also equal to our tau max. It's 43. Okay. And if we go through that, right, if that's our tau max, right, this is a 90-degree angle, right? So here our phi is equal to 90 degrees, right? But if we go back to what we talked about before, right, everything on the Morse circle is 2 phi. So all we're doing is we're taking the 90 degrees, dividing it by 2, So that phi is going to be 45 degrees, right? Which makes sense for this problem, seeing that we just have these values and there's no shear added, right? So the max shear should just be at 45 degrees. Okay. So now if we go into the second part, we've solved for max shear. Now we need to solve, we need to double check some of these things. We need to solve couple other values that they're asking for. So sigma x1, and they also, let's see here, want tau x1. Okay. So all this is we're looking at things with an angle, right? So sigma x would just be if there was no slope, right? But we're looking at it with a slope on there. So we're just going to be continuing, we're going to be using the sigma x plus sigma y over 2, so that's our average, and then we're adding the fact that it's an angle, cosine, and then in our case it's the 2 theta, if we're considering our theta the value that we solve for here. So it's 2 theta, which is the 43.6. Okay, so now if we solve for that, I gotta clean that up. We are going to get a value of negative 17.2 megapascals. Okay, and then if we are solving for our shear at that angle, right, x1, y1, we are going to get our R value, which remember is our shear max, and now we're looking for the shear at that angle, which is just going to be sine beta, right? And we notice right here, this is beta, right? So, which is just our 2 theta. So that is going to be our 43, and then sine 43.6. Okay? So if we solve for that, we are just going to get 29.65 megapascals. Okay? And that is how you do that problem.